Day 2, polar equations. Converting equations, polar to rectangular, and vice versa. All right, so first we'll do a little warm up together. All right, I want you guys to plot these points on the polar grid. All right, so the point 4 comma pi over 2. All right, the point 8 comma pi over 6. And the point 8 comma 5 pi over 6. All right, so for 4 comma pi over 2, we'll start at 0 radians, rotate pi over 2, and then move 4 up. All right, so that's the same point as 0 comma 4 on like a rectangular grid. All right, and then 8 comma pi over 6. All right, so now you would rotate pi over 6, which is 30 degrees, and then move 8 along the radius. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So that would be 8 comma 5 pi over 6. Now, just to show you that that's going to have the same y coordinate in terms of like a rectangular grid as the first point that we plotted, because if you think about it, if you drew like a triangle here, all right, that length is 8. All right, that's an 8, trust me. And then this angle here is 30 degrees. So this is like a 30, 60, 90 triangle where the hypotenuse is 8. So like the short leg is 4. So this point in a rectangular grid is still like 4 units above the x-axis. All right. Just to kind of point out the connection between the two x and y axes. And then 8 comma 5 pi over 6. So you'd rotate 5 pi over 6 and then move out 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So like we know in algebra or pre-calc, like you can have a bunch of points and they can all lie on the same graph. All right. The same thing works with polar. All right. You can have polar equations and all these points will lie on the same polar equation, or you could think of them as x and y coordinates, and all these points, the rectangular form, will lie on that equation. All right, so if we draw a curve, or this would be a horizontal line through those points, all right, on an x and y axis, since this would be the point 0 comma 4 in rectangular form, this is the equation y equals 4 in rectangular form. So if we know that, then we can write a polar equation. And that's what we're going to do all period. So I'm going to kind of just throw some new stuff at you, and then we'll review it here, and then we'll practice it again. So recall that y over r is equal to sine of theta. So if we just fill this part in real quick, y is equal to r times the sine of theta. So when you convert from rectangular form, so x and y, to polar form, you could replace y with r times the sine of theta. And so that's going to equal 4. So if we solve for r, and you're going to see, just like we usually solve for y in rectangular form for a lot of equations that are in conic sections, we're going to solve for r, and then we can type this in the calculator. All right, so that means that r is equal to 4 over the sine of theta. So r is equal to 4 times the cosecant of theta. All right, so this is the polar equation, and this is the rectangular equation. And they're both going to be the same graph on their respective set of axes. Okay, so let me show you what I mean. All right, so if I just open up a new graph here. All right, if I graph f of x equals 4, that's the line y equals 4. Now you could change this entry. So if I hit tab, it'll show a function. If I want to type in a polar equation, I could change this from function to polar. So menu, graph entry, edit, and then polar. And notice how it's already solved for r. So since we have the equation r 4 cosecant of theta, or r equals 4 cosecant of theta, we could type that in 4 times the cosecant So trig, cosecant. And then the theta button is right by the pi. So if you hit the pi button, there's a bunch of like random math symbols. All right, theta is in there. Hit enter. And, you know, to trace, if we did trace. All right, now that is our polar equation. You can see the points on there. Now the calculator is going to put everything as like decimals, but so there you go. So we'll do more of that on the calculator, but that's, you know, you can test if you did this right by graphing both and seeing if they're the same graph. All right. So we're going to do this a bunch of times. The formulas that are going to be really important are y equals r times the sine of theta. X is equal to r times the cosine of theta. All right, we wrote that down yesterday, and that just comes from the fact that like cosine of theta is defined as x over r, and sine of theta is defined as y over r. So we just solve for r and we could get those. All right, r squared, we wrote down yesterday, is equal to x squared plus y squared. So when we're taking an equation in polar form and going to rectangular form, if we see an r squared, we can always substitute in x squared plus y squared. All right, and vice versa. If we ever see a rectangular equation like a circle that has an x squared plus y squared, we could sub in r squared. All right, so these formulas are important for substitution. And then tangent is y over x. So if you ever have y over x, you can incorporate tangent. All right, and we'll refer back to these formulas a lot. So to go from polar to rectangular, that means you got to replace r and theta with x and y. That doesn't just mean straight up like replace x with r and y with theta. Like you replace x with r cosine theta and y with r sine theta. And if you have r squared, you replace it with x squared, y squared. And if you have tangent of theta, you can replace that with y over x, all right? And then the other way just means, all right, if we're going from rectangular to polar, we got to get rid of x and y and incorporate theta and r. So let's do example A down here, and we're going to use these formulas. All right, so first it says convert this equation from rectangular to polar and then sketch it on both axes. All right, so here is the equation, x equals -9. So any ideas how I can convert that to polar? Hayden, yeah, idea.
Draw it like a normal linear equation and then take points for that and convert it or something.
That's not a bad idea. I like it. You could do that. So you could draw this and find the corresponding points that are polar and do it that way. That definitely would work. Winter? Nice. Is that what you're going to say, Corey?
Yeah.
Nice. Beautiful. Is that what you're going to say, Sami? Nice. Yeah. So probably an easier way at this point would be to just replace x with r cosine theta. So that's what we're going to do. So if you have like a horizontal or vertical line, and that's the first type of example that we'll do, and we did one in the warm up, and this one is the second one. If it's just a horizontal or vertical line, you only have x or y. Replace it with its equivalent polar form. So we're going to replace x with r cosine theta equals -9. All right, and so that means r is equal to -9 over the cosine of theta. So that's okay. You could leave it like that, or you can also write it as -9 times the secant of theta, because that's what 1 over cosine is. So if we were to sketch this on this set of axes, then we just have to use like our x or y intercept and then draw the proper shape. So this is a vertical line on either graph. It's going to be the same type of picture on either graph. It's just the points will be represented in different ways. So if we start at the origin and move to the left 9, and I don't think there's 9 circles here, so I'm going to make every box worth 2. So like 2, 4, 6, 8, 10. All right. So now, boom, we got a vertical line, and that's what that would look like. And that's the polar form, and that's the rectangular form. So sometimes like graphing the polar graph, it's much easier just to convert it to rectangular and then just graph that, because you know what x equals -9 looks like, holy bucks. But to know what this looks like at this point, I don't expect you to. But if you just convert it to rectangular, then you can see what that graph looks like, and then you just graph it with the same x and y intercepts on this set of axes. Okay. So let's flip the page. So we're on page 6. Page 6, we'll read some gossip columns and then we'll do some math. All right, so we got y equals 3x plus 5. So, first let's graph both of these so I can emphasize that like the best way to graph this, like this in polar form. So y equals 3x plus 5, how to graph that on a polar set of axes is to just graph it on rectangular first and then put the same graph here. So this would have a y-intercept of 5. And then you can use slope. But see, this is not a rectangular grid. See, these are all little rectangles here. This is like, these are like not rectangles, they're like parts of a circle. So it's important to find the x-intercept to help you graph it here. So the x-intercept would just be, if you plug in 0 for y, you get -5/3. So we're at 1, 2, so like right here, and then draw the line. So the reason why I did that is because on this graph, you want to graph it the same way. Go up 1, 2, 3, 4, 5. And then to the left, 1, 2, so somewhere in between, so -5/3. And then just sketch that graph. So lines are probably a little harder than circles to graph on this. But again, just use the x and y intercepts. And I'm saying that because it's hard to use slope because like, all right, you go down 1, but how much do you know, how do you know how much you go left and right when it's not a rectangular grid? Like you're going now across an arc, not straight vertically or horizontally. That's why I think it's better to find the x and y intercepts. All right, now let's convert this to polar form. So if it's a linear equation, all right, we'll do one of every type of equation that you need to know. So when you're doing the homework, like I'd refer back to these if you see a similar type. And so if you have a linear equation, just like the horizontal linear equations or the vertical linear equations, we're going to replace y with r cosine, or check that, r sine, and x with r cosine of theta. So we get r sine of theta equals 3 times r cosine of theta plus 5. Okay. Now, if you wanted to graph this on the calculator, we couldn't type it in like this because remember, the calculator just tells us to graph polar equations like r equals something. So we got to solve for r now. So this is where our algebra skills come into play. All right, to get r alone, because it occurs in more than one term, we want to bring everything over to one side that has r in it. So r sine and 3r cosine on the left, and then 5 on the right. All right, and then now to isolate r, we could factor it out. So r times sine theta minus 3 cosine theta equals 5. All right, and then just divide both sides by this remaining factor. So r equals 5 over sine theta minus 3 cosine theta. And that would be the polar form, the polar equation for y equals 3x plus 5. Now, let's say you were doing this on your own or on a test and you couldn't like check an answer key or something. All right, how do you know if that line is correct? Well, you could pull out your calculator and you could type in 5 divided by, and then put in parentheses, the sine of theta. Oh, I got a message. Let's see what it says. Let me type this in first. I noticed it this time because I looked at one of my 3 screens mid-lesson. And then if I go to a regular zoom, there's our line. You can see it has a y-intercept of 5 and an x-intercept of -5/3. So you can check your work with the graph. How do you know theta was in the last one? Like, do you mean theta instead of t? Or, so the question was, how do I know theta is in this one? But I'm just trying to clarify. Do you mean like, why did I use theta instead of like another variable? So yeah, so theta is the angle. So if we look, all right, so where did theta come from? Well, we know that y is equal. So what it means to convert to a polar equation means instead of having it in terms of x and y, you have it in terms of r and theta. So to do that, we replace y with r sine theta and x with r cosine theta. Now, how could you graph this directly using theta without like knowing what the rectangular form looked like? Just like any graph, like you could just plot points and see where they intersect. So like what you could do is plug in like a random angle. Like, so let's take, this isn't random, this is a strategic angle, but let's take pi over 2. All right, and you could do this for any single value of theta because like the domain is all real numbers here because it's a line, it goes left and right forever. So what the calculator is doing is plugging in like random values for theta. So for example, pi over 2, seeing what r is and then plotting that point. So when theta is pi over 2, we get r is 5 over, so the sine of pi over 2 is 1 minus 3 times the cosine of pi over 2, so that's 0. So we get r is 5 when theta is pi over 2. I wrote that backwards. So therefore, all right, to find a point on our line, we rotate pi over 2 and then go up 5. So like there's that point right there. All right, and then how did I get this point? Well, I mean, I just used this, but you could also just to see what the x-intercept would be. All right, well that's going to be when theta is either pi or 0. So because both those angles like lie on this are coterminal with this x-axis. So like, all right, if I plug in another point, like r equals 5 times the sine of 0 minus 3 times the cosine of 0. All right, we get r is equal to 5 over -3. So now I have the point -5/3, comma, oh wait, I plugged in 0, not pi. I meant to plug in pi, but it works anyway because look, if I go 0 degrees, so I'm facing this way, and I move -5/3, now I move here. So now I'm on the x-axis because theta is 0. But since r is negative, instead of moving forwards, I move backwards. Yeah, theta is an angle. Yeah, theta is just an angle in radians. So the question was, what does theta represent? Just like trig, it represents angles and angles in radians. All right. Okay, let's do another one. All right, so we got x squared plus y squared equals 9. All right, so this is a circle centered at the origin. All right, so we're gonna see that we can graph circles like centered at the origin in polar form pretty easily, and circles tangent to an x and y axis pretty easily. But other than that, it gets really complicated, and we're not gonna do that today. So like, I want you to keep in mind that it's not just any circle, that this here is a circle centered at the origin. And if it wasn't centered at the origin, it's a little harder to do. All right, so I know it's centered at the origin because I know that's the circle form, and I also know that the radius is 3. So if I were to graph this before converting it, all right, it's centered at the origin, radius is 3. So I move 3 in every direction and then draw the circle, and boom, there it is. Now, how do I write the polar equation? All right, when you're stuck, all right, now you could replace x with r cosine and y with r sine and then square it and like factor stuff and it would work. But if you ever have x squared plus y squared, all right, don't do all that work. It's a waste of time. We know that r squared is equal to x squared plus y squared. So we're just going to replace that. So if you see x squared and y squared, and you could group them together and add them, then we could just replace, x squared plus y squared with r squared. All right, and then we could solve for r by square rooting both sides, and we get r equals 3. Now, technically, r could be -3, because if you square 3, you get 9. If you square -3, you get 9. But when it comes to like polar graphs, like 3 versus -3, like just means instead of moving this way, 1, 2, 3, you would move in the other direction, 1, 2, 3. But it doesn't matter because like both those points are on this circle where the radius is 3. So if you have a polar equation that is just r equals something, it's just all the points that are, 3 units away from the origin. So it's going to be a circle because all the points the same distance from the origin are going to make a circle. That's the definition of a circle. So what do you think, someone want to tell me, if we had a circle centered at the origin with the radius 32, what the polar equation would be without having to do the rectangular equation? So here, this is the point I'm trying to make. So if I do polar, r equals 1, circle with radius 1. R equals 2, circle with radius 2. R equals 3, r equals 4. So like a polar equation that's just r equals a constant, it's just a circle with that radius and at the origin. Because it literally means just radius is 5. And if you look at the polar graph and find all those points, they make a circle. So r equals 32 is just the polar equation for a circle with radius 32. All right. So you can quickly write the polar equation of a circle if the center is at 0, 0, and we know the radius by just doing r equals the radius. All right, let's flip it. All right, these actually are in the right order, so we're on the right page here. All right, so now we have a circle that's not centered at the origin. So it's going to be a little different, but this circle is unique to just like any old circle because it's shifted to the left 3 and the radius is 3. So the center is at -3, 0, and the radius is 3. All right, so it's tangent to the y-axis. So this next part, D, is going to be like just how do you write circles that are tangent to the x and y axis. So we're going to go through it the long way first, and then on the bottom, in the middle of the page, you'll see like a shortcut. All right, so what do? Well, we got x and we got y. We don't have x squared and y squared. So the best that we could do is to replace x with r cosine of theta and replace y with r sine of theta. Okay. So then we can multiply this out. So we get r squared cosine squared. And then if you FOIL, you get 6r cosine of theta plus 9. So I just did the foiling in one step. So it'd be r squared cosine squared plus 3r cosine plus 3r cosine plus 9. But when you add 3r cosine to 3r cosine, you get 6r cosine. And then r sine squared would be like r squared times sine squared. And then equals 9. So when you just have an equation with x and y in it, and you don't see like x squared, y squared, or like any other things you can substitute in, then you just have to replace x with r cosine and y with r sine. Then multiply everything out. And what happens is these 9s will cancel out. So now we got a 0 on this side. And remember that the Pythagorean identity, sine squared and cosine squared equal 1. So if you ever have sine squared and cosine squared, see if you could group them together. So r squared cosine squared of theta plus r squared sine squared of theta, and then just 6r cosine of theta equals 0. So I just grouped these together because then you could factor out r squared and you're left with cosine squared of theta plus sine squared of theta. All right, plus 6r cosine of theta equals 0. And sine squared plus cosine squared equals 1. So just a general strategy when you're manipulating equations where that have trig functions in it, just like identities, that's why we do identities before this, you can use that to simplify things. And if you remember when we first learned identities, I described why do we have to know it. One, it's just like a good brain workout. If you could do identities and manipulate stuff, it's just good practice with like critical thinking and substituting. And it's just, if you know how to do that, you'll be able to learn other stuff. But also the reason why it's in this course specifically is because it makes calculus a lot easier. And polar is something that, this is pre-calculus, so we're starting to get into calculus stuff. All right, by knowing identities, you make your life way easier. And watch what happens. If we know sine squared plus cosine squared equals 1, boop, that's gone. And that's a math term, boop. So we get r squared plus 6r cosine theta equals 0. All right, so we just simplified this to this. All right, then what you're gonna do, so when you have like an r squared and an r, and it's like set equal to 0, all right, factor out an r. So again, this is algebra stuff. So all those times when like you ask, why do we need to know this? It's all building towards learning calculus over the last like 2 years. All right, so this is now like a quadratic function where you have two things being multiplied set equal to 0. So you can set each factor equal to 0. And now r equals 0, we could just kind of ignore because like that's really nothing. That's just like a point at the origin. So again, we simplified this down again. And now we have r is, if we set that equal to 0 and subtract 6, we get r equals -6 cosine of theta. And that would be the same circle as that. So it has a center at 3. So we move left 1, 2, 3. And it has a radius of 3. So it's the same circle tangent to the y-axis. And so in general, without having to do all these steps again, how can we quickly write the polar equation of a circle tangent to the x or y-axis? Well, we just saw that for cosine, it's tangent to the y-axis. And like plus means it's going to be to the right. Minus means it's going to be to the left. And that number is going to be the diameter. So see, this still had a radius of 6, but it's like 6 all the way this way. And if you were to plug in different values for theta, it sort of makes sense that it ends up here. Because like if you plug in pi, so if you plugged in pi for theta, the cosine of pi is -1, so r would be 6. So if you started here and rotated pi and then move 6, now you have this point here. All right. And for any other angle on here, like if you plugged in pi over 2, the cosine of 90 is 0. So you rotate pi over 2 and you get r is 0. So then you'd be right here. And then for any other point, like you rotate a certain amount and you would land on the circle. All right, and then for r equals plus or minus a number times sine of theta, that's on the x-axis. All right, any test that we'll take is open note, so you can just like refer to this. All right. Okay. E, now we have a circle that the square isn't completed. So we could complete the square and put it in this form, but we don't have to. So let's just put it right into polar form. And it might be easier because then if it turns out to be like one of these, then we know it's going to be tangent to the x or y axis and we'll know the diameter. So notice how we have x squared plus y squared all alone here. So we could replace that with r squared. And then we also have y, and y is equal to r sine of theta. So we could do that too. All right, now we just have two terms with r in it. So we could get r alone by factoring it out. So by factoring out r, you get r times r minus 13 sine of theta. And then you could set each of these equal to 0. All right, so r equals 0, that's once you get that, that's sort of irrelevant. It's just like nothing, it's just like a point on the origin. And then this becomes r equals 13 sine of theta. So that means that this, now I should be clear, when I write x-axis and y-axis, like if it's r sine of theta, it's tangent to the x-axis. And r cosine theta, it's tangent to the y-axis. But I was sick. I used this g into an arrow. I didn't even mean to do that. All right, so this will be a circle tangent to the x-axis with a diameter of 13. So if you go 10, 11, 12, 13, here and here, then just make a circle. All right, so the center would be in the midpoint there, so like 6.5. And then here, if you go make each thing worth 2, so like 2, 4, 6, 8, 10, 12, 14. So right here, that's what it looked like on the polar grid. I just did it different scales. That's why it looks smaller, but it's the same diameter, same radius. Can you divide by r in the third step when it's outside the parentheses? I guess it would give you the same outcome if you divided by r, but it's never good to divide by a variable because the variable could be 0 and you can't divide by 0. So it's always better to factor out the variable and set it equal to 0. And it essentially gives you the same thing, but in general, you don't want to divide by variables because you don't know what they equal. All right, one more page here. All right, so practice, but because we're low on time, I'm just going to practice with you and highlight all the good stuff we just did. All right, so practice converting from polar to rectangular. So to go the other way, all right, we want to look for like r sine theta, because we know that's equal to x. All right, we want to look for r cosine theta because we know that's equal to y. We want to look for r squared because then we could sub in x squared plus y squared. And, you know, we could look for, if we have tangent of theta, we can always plug in y over x. All right, now sometimes, and this is going to happen in 2 examples, we must square both sides. Because we want to get r squared. Yes?
What? I thought r sine, like, theta equals y. Is it the other way around?
Yeah. Thank you. My fault. So correct that. My fault. So r sine theta is y, r cosine theta is x. It's an if you forget, like I just did, or just wasn't thinking, it's an alphabetical order. So like x is before y, cosine is before sine in the alphabet. Good catch. Thank you. All right. So to convert this one here, r equals 3 cosecant theta, we have to try to get r sine of theta or r cosine theta. So if we divide both sides by cosecant, we get r over cosecant equals 3. And then r times the sine of theta equals 3. Because 1 over cosecant is equal to sine. And then now you can just substitute this out for y, and you get y is equal to 3. All right. Now, if we work down 1 to here, r is equal to 7. So we have what r sine equals. So, I mean, technically you could plug in like y over sine, but that wouldn't help because you're not eliminating like r or theta. Same thing here. We know r squared is equal to x squared plus y squared. So if we had an r squared, we could sub this in and we'd get rid of r and have no theta and immediately put it into rectangular form. So what we could do is square both sides. So when you need an r squared and you only have an r, square both sides. And now we have r squared is equal to 49. And now we could replace r squared with x squared plus y squared. So we get x squared plus y squared equals 49. And now that's our rectangular equation. All right, same thing here. We don't have r times the sine of theta. We have 20 times the sine of theta. So what we could do is instead of squaring both sides, we want to get r sine theta. So this is lacking in r. And this is r. It's also lacking in r. So that we could sub in r squared. Or x squared plus y squared in for r squared. So here, we're going to multiply both sides by r. And then it'll make it nice and allow us to plug stuff in. So then we get r squared is equal to 20 r sine of theta. And then for r squared, we could plug in x squared plus y squared. And then equals 20. And then for r sine theta, we could plug in y. And then that's just a circle that's tangent to the x-axis. So if you wanted to put this in standard form, you just have to complete the square. But it's already a rectangular equation because we got rid of x and y. So this is fine if that's all we got to do. If it said write it as a rectangular equation and then put it in standard form, then we'd complete the square. All right, and then another strategy. So again, refer to this if you get stuck on a homework question and just ask me for help too. That's also an option. Another strategy you could do is if you have like a ratio set equal to r like this, you can cross multiply. So you get r sine theta minus 5r cosine theta is equal to 7. And now what's beautiful about that is now we have r sine theta, r cosine theta, and we can replace r sine theta with x and r with y, sorry, and r cosine theta with x, y with r sine theta. And then there you go. And then if you want to put it in point slope form or slope intercept form, there it is. All right, so that's how you convert. Now, the very last thing, I want to look at this on our calculator. So r equals 2 sine of theta. This is pretty cool. And we're going to do a whole day on these things. All right, so if I type in sine of not theta, so let's see, if I just type in sine theta, see what happens. All right, it's a circle tangent to the y-axis. All right. Now, if I cut the period in half, look at that. That's pretty cool. That's called a Rhodes curve. And we're going to do that next week. Now, do you think, just by looking at the graph, do you think it's easier, and I can zoom in a little bit. So make a prediction. Do you think it's easier to work with the polar equation, r equals 2 sine theta? Or do you think like the equation in terms of x and y is more simple or something like that?
Polar.
Yeah, that's a good guess. I agree. So let's see what the rectangular would look like. Yeah, so sometimes polar is easier, especially when you have like crazy stuff like that. So how would we convert this? Well, first, and again, I wouldn't ask you to do this. This is just to see why we don't, sometimes we're going to keep things in polar. All right, first I would use the double angle formula for sine. All right, then you could take sine. Oh, so then you have to multiply both sides by r. Not yet, my fault. So then we could take sine of theta and replace it with y over r, because that's the definition of sine. And cosine is x over r, all right? So we didn't quite put it in rectangular form yet, but we got rid of theta by putting the actual definitions for sine and cosine. So that's gonna be r equals 2yx over r squared. All right, which means, well, if r squared is equal to x squared plus y squared, which we could sub in for r squared, then r is the square root of that. That would just be the square root of x squared plus y squared. So you can see this is kind of this messy equation. Like you could even write it like this, where if this is x squared plus y squared to the 1/2 power, and that's 2yx over x squared plus y squared. And then like you cross multiplied, you would get 2yx equals x squared plus y squared to the 3/2 power. So see, that's like a really messy equation. So the moral of this story here in the second half of the last page is like, sometimes it's just easier to leave it in polar. All right, so this is what we'll do after Monday. So I guess Wednesday, we'll look at these Rhodes curves. All right, so I'm gonna end the video and tell you what you need to do.